Hey everybody, welcome back. In this section, we're looking at dot product, directional angles and orthogonality. Let's just jump right into it. Let's start with an example. I want you to sketch and find the dot product of u is the vector 4, 0, and v is the vector 0, -3. And then once you've sketched it from the dot product, what can the dot product tell you about the relationship of the two vectors? Pause the video and go ahead and work that out for a second. Make sure you understand everything for the dot product from earlier. Okay, assuming you've done that, u is straight along the x-axis, 4 units. V is straight down along the y-axis, -3 units. And we find doing the dot product that u dot v equals 0. And so that cosine theta is also 0. Why? Because u dot v is magnitude of u, magnitude of v, cosine theta. And if u dot v equals 0, and we know the norm of u is not 0, and the norm of v is not 0, clearly cosine theta's got to equal 0. So we've got cosine theta equals 0, theta equals pi over 2. And we can see from our picture and also from our cosine, a 0 dot product reveals orthogonality. Orthogonality is perpendicularity. So two vectors that are perpendicular to one another are called orthogonal vectors. And what happens if u dot v is -1, not 0? Ignore that picture for a second. If u dot v is -1, then we have cosine theta equals -1. And u and v are opposite vectors. So they point in the opposite direction. Now, and I said orthogonality or orthogonal vectors, we have some terminology. If two planes are perpendicular to each other, we just say they're perpendicular. That's what this sketch is for. So that's this plane. One plane is intersecting another plane. The intersection of two planes is a line. We'll be covering that in later sections. When two vectors are orthogonal or perpendicular, we say they're orthogonal. And when a vector is orthogonal to a plane or perpendicular to a plane, like in the picture here, we say it's the normal vector for the plane. Okay, so there's 3 terms for perpendicularity. That's a fun word to say. Actually shows up in the book series by Brandon Sanderson. I'll tell you about it sometime. Let's look at the direction angles. If I've got a vector v from the origin in 2 dimensions, and I've got angle alpha here and angle beta here, if we use the dot product just on alpha, notice that we have v dot I, cosine theta or cosine alpha equals v dot I over the norm of v and the norm of I. I is a unit vector, though. It has a length of 1. And if we dot v with I, all we get is the v1 component. The v2 component is zeroed out because there's no there's no y component to the I vector. So cosine alpha is just v1 over the magnitude of v. We could use the same thing with do sine to get the other part of it, sine of alpha, but I'm not doing it. I'm going to use cosine of the other angle beta because you'll see in 3 dimensions, sticking with cosine makes more sense. We're going to do the same thing. We're looking at v and j vectors. So we can, the cosine of beta is v dot j. And that's going to isolate the v2 component because j is 0, 1. We got 0, 1 here. We got 1, 0 here. So 1 times v just gets us v2. Magnitude of j is just 1, so we're left with v2 over v. We can see that the directional angles are related to the individual components over the magnitude of the vector. I know a lot of people say beta, but it's really beta. It's where alphabet. Found that out in my graduate mathematics class when one of the Greek students was making fun of the teacher for saying beta. She's like, you're saying it wrong. It was great. If we jump this up to 3D, you'll notice, so I've got a vector v here. It's going in 3 dimensions. Alpha is again from the x-axis, so I kept the picture the same. Beta is again from the y-axis, so this picture matches up. And I think that's phi. I used phi there just because it's easy for me to draw. And that's off of the z-axis to it. But it's the same story. We do v dotted with the unit vector that goes along the axis to get the z component. B dot k, we get v3 over v. So to find the directional angles, find the inverse cosine of each component divided by the norm of v. So we would take cosine inverse to find phi. You might find this helpful. Cosine squared alpha plus cosine squared beta plus cosine squared phi equals 1. And if you don't like my picture, there is a picture in the book. What page is this? This is on page 693 in the book. And they did the same thing. So alpha is the the vector going to the I hat. Beta is the vector and the j hat. And what is that? Capital gamma. I need to learn my Greek letters a little bit better. B going over to the k hat direction does that angle. And the formulas are all the same. That's it for this one. Peace.